tau, that is the Laplace of f of tau and multiply with the g of t minus tau going to be multiplication of f of s and g of s. This is the convolution theorem. And we need to prove that convolution theorem that this is true because this is the convolution theorem. Why do we need to study convolution theorem? Look, if we compare with the sheet function theorem said that the exponential function will be multiplied with the
Sir, Abu Rayhan Rana is waiting for joining, sir.
of tau and g of t minus tau as one shift function, right? So usually shift function have the exponential of the delay time with the original function, the Laplace of original function. But in convolution theorem, it is seen that the both Laplace of both function will be directly multiplied. So there is no exponential function. That is the difference from the shift function theorem. Understand? So in by meaning, you see, if it is the function derived from two given functions, by integration that express how the shape of one modified by the others. See, that means it's supposed to be, if we have this kind of function, Laplace will be f of s into e to the power minus s tau and g of s, right? If we follow general and the shift function theorem, then the result should be like this. However, the convolution theorem said no, the Laplace of those function will be directly multiplication of Laplace transform. Okay, you see, so this is not necessary in convolution theorem. That's the significance or the beauty of this convolution integral theorem. Understand? Hello? Everybody understand? Why
Yes,
we
sir.
need to study convolution theorem?
Yes, sir.
Okay. Now we'll see the proof of convolution theorem. The f of tau, two different functions, and we can write the Laplace of f of tau, g of tau, multiplication form convolution. Then we'll show here. So you can see the f of tau, g of tau, their convolution will be minus infinity to infinity, f of tau, g of t minus tau d tau. This is right. So we can report this function is minus, this is the Laplace, okay, this to this is the Laplace transform, and this is the original function that we have already in the first line. You see, after that we separating time dependent and tau dependent, t dependent and tau dependent, two variables here. So we are separating those variables, okay. So we take out tau, and we have only the t, this one, and inner side function or integration is totally a sheet function theorem we can apply here, okay. The g minus g of t minus tau, we can write in this form. Look, this same right. So we can apply the sheet function theorem. Then we have got e to the power minus s t g of s. Now we are putting again in the equation that f of tau g of s e to the power minus s tau d tau. Now g of s taking out from the integration. So we have this form, minus infinity to infinity f of tau e to the power minus s tau d tau, okay. Then what type of Laplace transform this part? Bilateral or unilateral? Under the circle, under the, what kind of Laplace transform this?
Sir, the bilateral, sir.
Yes, thank you, Jim. It is bilateral. So now we, since it has f, so we can write f of s, and g of s already existed. So we can write f of s and g of s. So the theorem is proved. Theorem is proved. Everybody understand?
Yes, sir.
Yes, sir.
Okay, thank you.
Yes, sir.
Now we will see some application of convolution theorem. So we are going to apply this convolution theorem in real life practice. Like in our system, we always used to use a machine, right? Motor, generator, or the power supply, or any kind of the, like, if you want to do some work, so you need to use the machine. So machine has two things mainly. One is input, another one is output. If there is no output, then how can we say that is machine or that is everything has, even human being has output, understand, because they are working, and input is food. So because of food they are working, understand, food is energy, right? So that things, so output, if you want to have the output, then the here process occurs. You are giving the raw material and machine process and give the product, understand, if you go for the real practice. So in this machine process system, so process has also a transfer function, and input has another transfer function. If we multiply these things, then we will get output. That is the convolution theorem. So here has two examples. One is an unknown relaxed linear system has impulse response h of t equals to u of t minus 1. That means there are two functions here, right? One is u of t, that is unity step function. Another also unity step, but delay occurs, 1 second delay. T minus 1 second delay occurs. Then find the response to the input signal f of t when the 2u of t minus 1 using convolution theorem and transform. So convolution theorem showed that multiplication of Laplace transform individual function, that is g of s, f of s. Understand? So h of t, if we convert into Laplace term, because this is given in time domain, if we convert into Laplace domain, then capital H of s equals to, this is gonna be what? 1 over s minus, it has the delay 1 second, right? 1 second delay, so it is e to the power minus t and 1 over s. Understand? And f of t is 2u t minus 1. So if we convert into Laplace domain, then capital F of s and 2 into e to the power minus 1 over s. Here is the shift function. This is the shift function. So we need to convert it into Laplace domain by applying shift function theorem. Then we apply the convolution theorem, the h of s and f of s multiplication. That means you will multiply this and this. These two Laplace transform will be multiplied. Okay. After multiplication, we are getting that 2 e to the power minus 1 over s square minus 2 e to the power minus 2t 1 over s square. It is very simple. Look at here. If you multiply in the first term, then 2 e to the power minus t 1 over s square. Second one is e to the power minus t and e to the power minus t. So it becomes e to the power minus 2t. And s is 1 over s square, 1 over s square multiplied. So this is. Okay, everybody understand this multiplication?
Yes, sir.
Yes, sir.
Yes, sir.
After that, we are applying inverse Laplace transform. After that, we apply inverse Laplace transform. And that inverse Laplace transform says that, because our target, what is our target? To find out the response of the input signal, this one. Response always, remember this is a thumb rule, response always in time domain. Understand? Response always in time domain. So we need to convert into time domain. So this is the Laplace transform, we apply inverse Laplace transform. That is the, we converted into time domain. So h of t, f of t going to be 2 is constant itself, and e to the power minus t 1 over s squared, basically this one. If you see the table, I already have given you the table. So 2t u of t minus 1 and minus 2 t u t minus 2. Okay, that means the first 2t is fixed, same. But here, one more second delay occurs because earlier was 1 second delay, right? But in seconds, after multiplying the both, what is called that function, then we got the another second delay occurs, t minus 2. Okay, t minus 2. Everybody clear about how can we use convolution theorem? Very simple. If we multiply this one and this one, is it possible to find out this? Because it's going to be the 2u of t. It is quite impossible. But you can apply geometrical explanation. But if you apply the convolution theorem, it is easier than geometrical explanation. Understand? Next example, if you see here, another unknown relaxed linear system has impulse response h of t equals to a minus b e to the power. Here will be e to the power minus at, and input signal has e to the power minus bt u of t. Then it says the y of t equals to h of t and v of t. That is multiplication of both. Then h of t e to the power minus at u of t, we can find out the a e to the power minus at u of t minus b into e to the power minus at u of t. So if we apply Laplace transform here, then what we got? A and e to the power minus at, what is that? S 1 over s plus a. B is multiplied, so b. And e to the power minus at is 1 over s plus a. After that, rearranging the equation, we got the a minus b divided by s plus 1. F of t gonna be f of s equals to e to the power minus bt, so 1 over s plus b. Then apply the convolution theorem. A minus b over s plus a into 1 over s plus b. After that, what we got? Look at this. S plus a into s plus b. Then what happened? Is a, right, minus or plus ab, isn't it? Oh no, wait. This is the multiplication, s minus b divided by s plus 1, s plus b. Now we are applying, what is this? Partial fraction expansion. Everybody remember partial fraction expansion? Everybody remember partial fraction expansion?
Yes, sir.
Partial fraction, f fraction expansion. That has been applied here. Okay. Then we found 1 over s plus b minus 1 over s plus a. Now we are applying the inverse Laplace transform. Then what we got? This and s plus b in inverse Laplace is e to the power minus bt u of t. U of t unit step function whose value is 1, and minus 1 over s plus a. So e to the power minus a t u of t. Okay. This is the thing. Now tell me, who did not understand? Everybody understand?
Yes, sir.
Clear, right?
Yes, sir.
Now we are applying the inverse Laplace transform. Another topic, that inverse Laplace transform. The objective of studying inverse Laplace transform is to find the response of the system, or if the function or the transfer function, whatever you say. If we want to find out the response, then we must apply the inverse Laplace transform. So inverse Laplace transform by definition says the equation. This is the equation of inverse Laplace transform. However, it is more easier than this equation will be in the here. We need to apply the partial fraction expansion. So firstly, we must know the transfer function, which has the poles and zeros. Roots of denominator. There are two parts, right? One is above the reference line, another is below the reference line. Above the reference lines are called zero. Okay, and below the reference line called poles. Okay. The roots of denominator are called poles, and roots of numerator are called zeros. And these are very important, not only for this course, but also for the control engineering course. But you must know the poles and zeros to make the system stable, because pole zero can make the system stable or faster or dynamic. So you must know what are poles and zeros. Usually poles, you know that every houses has poles, right? There are 4 poles or 5 poles, 6 poles, or whatever. Needs to make the house balance. So in the system, we need to have some poles that will accelerate the system. That's why poles are important. And from there, we made this rational fractions. This is called as the partial fraction expansion. To solve this transfer function or find out the factorization, we have 5 ways. One is called the distinct real pool, another one is repeated real pool, and complex pools, another one is exponential numerator, because pools we know, but there is the exponential numerator, and another improper function method. Improper function method means the m is higher than n. The above, if it is n, means the if s to the power 4 is the highest power of the numerator, and s to the power 3 is the highest power of the denominator, then this kind of function is called the improper function. Understand? Because here is a usually denominator has highest power. Highest power. But in case if the denominator has lowest power, then we call it improper function. If I give you one example, that we used to get the exam marks in terms of 100 to whatever you obtain, right? Like 80 by 100. That means you receive 80 within 100 marks. But if you achieve 110 marks within 100, it is improper, right?
Yes, sir.
Yes, sir.
So improper function, if it is occurred, then we have to verify another way. So let me explain this distinct pool and repeated real pool or complex pools. The distinct real pool is the real pool. Everybody understand? Which has no any? Can you turn off your microphone? Which has no any y-axis value. All are in x-axis because x-axis is the sigma and y-axis j omega, imaginary. So real pool means it should be in the
X-axis.
and repeated real pool. The same, the pool is real, but the same pool coming again and again. That is repeated. Then we have complex pool. A complex pool which has x and y axis both values, like a pool situated here, whose value is something like that 5 plus j 2, 5 plus j2, then it is called complex pool. We will see this next slide. Can you take a look? Distinct real pool example, repeated real pool example, complex pool examples. Can you see?
Yes, sir.
So do on your khata these things. Can you write it now?
Yes, sir.
Please write. Are you doing the problem?
Yes, sir.
Okay. Can you find the A and B value in the first problem? A and B value. Can you find it? So everybody, are you doing? Hello?
Yes, sir.
Hello?
Yes, sir.
जी सर.
If you cannot do now, these are your homework. Tomorrow you will show.
Okay, sir.
Okay, tomorrow in the class, everybody should show what you have done. That is the task. So improper function, an exponential numerator, and all the things tomorrow you can show me. So this is your homework.
Okay, sir.
Okay, tonight you will solve. So this is what now the homework number 2 or 3. This one.
Sir, homework number, sir, 2, sir.
2. Yes, homework number 2. So tomorrow you have to show in the class. I'm telling you. Who cannot show, the attendance will not be given for them. that thing's going to be studied from now. We know voltage source, we know current source, and we know resistor, inductor, and capacitor, and their voltage drop. Right? Everybody knows these equations and the
Yes, sir.
sources. Now, if we look at the right side, then the Vt becomes capital V of S, It becomes capital I of S in terms of Laplace domain. R constant itself, S IR, the current, because the resistive current, that becomes the I of R is, that means the drop of resistor drop in terms of Laplace domain is capital R IR S of S. In case of inductive drop, voltage drop, that SL, because since it has a derivative function, so it will follow the first derivative Laplace transform, so that we can write down. I already have discussed in the class that what would be the inductive voltage drop, right? When we do the derivative function Laplace transform, that time I have discussed. So we got it. After that, in integration, we have also discussed the capacitor voltage. So now I think it is easy for you to understand that why do we need to study the first derivative Laplace transform and the integration, Laplace transform, integration function, integral function. Now you see the application of them here. Do you listen clearly?
Yes, sir.
Yes, sir.
Sir,
Now here is the one problem. Okay.
Sir, no more today, sir.
You see how many days we have class?
Sir, still 4-5 class left, sir. And only 20 pages are left, sir. And also, sir, big transformation.
Only how many slides?
20, sir.
20.
Yes, sir.
So we have to finish. We have to finish within Monday. Understand?
Monday. Sir, we have extra another class, sir. You will took, sir, this next Friday. 2 hours, sir.
Okay, that is okay. But the problem is, if we cannot finish early, how can we revise? And how can we have review class?
You do it, sir. Okay, no problem, sir. Carry on your class. We are attended.
The thing is that you must know the everything, because I don't know what will come in the exam, right?
স্যার আজকে অনেক গরম স্যার ফোন টোন সব গরম হয়ে যাইতেছে স্যার